Hey guys, my name is IBM, and today I've decided to introduce another unit of AS physics, and this is going to be a deformation of solids. Consider leaving a comment behind if anything is not clear. I can always try my level best to try and rectify it. So today we are going to deal with the second topic of AS physics, and that is deformation of solids. Having done particle physics, these topics are not in the same order as they are being taught in class. I just do them the way I want my students to view them. So the way I want, because I want my students to be viewing topics which are ahead as I teach the topics, as I teach the first topics. Okay, so do not forget, this is the Cambridge International Education Curriculum, and this is going to be AS. Okay, so this is going to be a deformation of solids, and I think this is going to be lesson number one. It's deformation of solids. That is going to be lesson number one. And of course, just to give you a clue of what we expect in deformation of solids, we expect concepts about force and deformation, Hooke's law, elasticity, combination of springs. We expect stress, strain, and Young modulus. We expect elastic potential energy, and of course an experiment to describe Young modulus or to obtain Young modulus, and so on and so forth. So this is a very short unit. I think it will be approximately 2 lessons. I'll try my level best to just make these 2 lessons. If you're a teacher, you should be able to teach this in 2 lessons. That is at most 2 hours, at most 2 hours, because this is a very short unit. Okay, so let's dwell into deformation of solids. We know the meaning of the word deformation, to deform something, you know, and we are going to be looking at energy stored in a deformed material to understand what we mean by deformation. So what do we mean by deformation? So when a force is applied to a material or a body, its shape is expected to change, its size is expected to change. The body may compress, it may stretch, its shape may change, may be squashed, and so on and so forth. So this change to the shape, size, or nature of the body is what we call deformation. The change in shape or size or structure of an object after a force is being applied is what we call deformation. So when we say material has been deformed, it's because the force has changed its size or its shape, so it is being deformed. So deformation is going to be in 2 directions. There is that deformation which in most cases is going to stretch the object out. This is because a pair of forces are applied to the object to stretch it out. So we say the object is under tension. Then we shall have a deformation where the forces push towards the object. In other words, the forces tend to squash the object. So in that case, we say the object is under compression, or the deformation is going to be a compressive deformation. So There are going to be two types of deformation that we are going to talk about. That is the compressive one, act um, where the forces act to pull apart the object. That is the compressive one. I mean the tensile one, and where the forces act to compress or to squash the object, which we are going to call the compressive. So when, for example, a wire is bent, some parts become longer and in tension, and others become shorter and are said to be under compression. If you walk on a bridge, for example, the bottom of the bridge, it's like the bridge bends upwards because at the bottom, the parts of the bridge at the bottom tend to pull apart. So we say the bottom of the bridge is going to be under tension. But at the top, the parts of the bridge on the top of the bridge tend to move closer to each other. That means we say the bridge is under compression on top and under tension at the bottom. So it illustrates tensile and compressive forces effects on an object. We can just consider the diagrams below. So for compression and for tension, for compression, the forces act in opposite directions on the body. So the object under the action of tensile forces becomes longer and it is supposed to become thinner because the diameter or the cross-sectional area decreases as the length of the material increases. So if the same material is stretched out, its cross-sectional area decreases. So we say it becomes longer and thinner. And if the object is squashed without buckling, if it doesn't buckle, we expect the object, which is under the compressive forces, to become shorter and thicker. So a simple demonstration of these two a simple demonstration of these two can be illustrated by this. If you try to break a stick, you try to bend a stick to break it, it will easily develop a crack on the top. It will easily develop a crack on top because the particles on top are being pulled apart by the tensile forces, and it is, of course, the particles at the bottom are being pushed together by the compressive forces. So on top we have tension, at the bottom we have compression. Another demonstration was with something similar to a bridge. As cars move on top of the bridge, they exert forces on the bridge, and at the bottom, the particles, the material making up the bridge at the bottom develops easily cracks because tensile forces act on the bottom of the bridge and compressive forces act on top of the bridge. So a compressive force is going to cause the material to become thicker and shorter, or it is going to become squashed. And a compressive force is going to cause the material and the tensile force is going to cause the material to become longer and thinner. So we now know the meaning of the word deformation. A material is subject to an applied force which causes the material either to change its shape or change its size. It may change shape by becoming shorter and thicker, or by becoming longer and thinner, and so on and so forth. So that's what we mean by deformation. That's why this unit is going to be called deformation of solids. Okay, so let's now look at force and deformation. Let's compare forces and deformation. A simple demonstration of force and deformation will be if we consider the animation. I don't know whether my animation is looking good, but it is kind of distorted. So let's consider this animation here. If a weight is attached to a hanging spring like this one here, the spring is expected to stretch. That means its length is expected to increase. Of course, this increase in length is what we call the extension. The increase in length is what we call the extension. So as the spring is loaded with some forces or with some weights, the tension in the spring is going to increase. That's why the spring is actually going to extend. It is going to increase in length. So we say the spring has been deformed by adding a load or adding a weight. So the weight is going to be the deforming load, or the load, or which is going to result to a force because weight is a force. And The stretching of the spring is going to be what we are going to call the deformation of the spring. So the spring is said to be deformed if we attach a force or a weight onto the spring. So if a weight is attached to a hanging spring, the spring stretches and the length increases. And I've mentioned that the increase in length of the spring is what we call the extension. The increase in length is what we call the extension of the spring. And the weight which has been attached here, the weight is going to be called the load. So every time I talk about the load, I'm referring to the force. Every time I talk about the load, I'm referring to the weight which is causing the material to stretch. That is going to be the load. So if we increase the load, as the load is increased, the extension also increases. So we have a small extension when we add one load or one weight, and the extension becomes even bigger if we add two loads or two weights. So it's like the load is somehow directly proportional to the extension. As the load is increased, it's like the extension also becomes bigger. That is what we shall call Hooke's law later on. However, for small loads, if the load is still small, for small loads, when the load is removed from the material, the spring is expected to return to its original length. As you can see in this animation here, I hope it is visible. If the loads we are considering here are still small, when we remove them, the spring is expected to return its original length. The original length or the original position is this point here where we have this red line here. So when the loads are removed, if the loads were small, we expect that this material should return its original length. And if a material returns its original length, then that material is going to be called elastic. And the change it has undergone is going to be called elastic deformation. So in that case, I'm saying the spring is said to have undergone elastic change or elastic deformation. If the loads used are very small or relatively smaller, when we remove the loads from the spring, it returns to its original length. If the material returns to its original length, we say it has undergone an elastic change or it has undergone an elastic deformation. So in other words, what I'm saying is that elastic deformation occurs or is when the deforming force is removed from a material and it returns to its original length. A material is said to have undergone elastic deformation if when the deforming load is removed or when the deforming force is removed, the material returns to its original length. So it is said to have undergone elastic deformation. So in an elastic change, a material returns to its original length when the deforming force on it is removed. This is very important. In an elastic change, or called elastic deformation, a material returns to its original length when the deforming force is removed from it. A good example is going to be copper. Most of the wires, the electrical wires at home, I think are made out of copper. Most of the springs in the laboratory are made out of copper. So when the deforming force is removed, the material returns to its original length, but this is only possible if the loads that were used were relatively smaller. And if the loads are still small, of course, we know that as we increase the load, the extension is expected to increase. That's why we are saying the load is directly proportional to extension, and that's what we shall later on call Hooke's law. However, if the load is increased greatly, if I was to use a very big load onto the spring, then removing the big load from the spring may have an effect on the spring that it may remain with some extension even when the load is removed. So I may find out that when I remove the load, the spring only stretches, but it may not go back to its original point. It may not go back to its original length. So in that case, we say the change was permanent or the material was permanently deformed. So if the load is increased greatly, the spring will change its shape permanently. So it undergoes what we call permanent deformation, or which we shall later on call plastic deformation. So on this slide, we have now noted that elastic deformation means that when when the deforming force is removed from the material, it returns to its original length. That is when we say it was elastically deformed. Later on, we are going to see if it is not elastically deformed, perhaps it is plastically. The opposite is going to be plastic. Plastically deformed. We shall talk about plastically deformed. If it is not elastically deformed, perhaps it is plastically deformed, because in that case, when the deforming force is removed, the material will not go back to its original length. We say it retains some extension. It retains some extension, or it retains some deformation, even when the deforming force has been removed. That's what we shall call plastic deformation later on. But for elastic deformation, for small loads, increasing the load increases the extension. However, if we increase the load greatly, then the material undergoes a permanent change in shape. Therefore, a graph of, say, extension, or a graph of force against the extension of the wire should take this shape here. So if I was to sketch a graph of, say, extension against load, or load against extension, when I talk about load, I'm referring to the deforming force. Then the graph is going to take this shape here. For small loads, if the force is smaller, the load is directly proportional to extension, which is giving us a straight line from 0 up to point P, or from O up to point P. That is for small loads. The load is directly proportional to extension for small loads. However, we can still increase the loads to an extent where the load will no longer be directly proportional to extension, but when we remove the deforming force, the material can still go back to its original length. At the point where the load is directly proportional to the extension, we say Hooke's law is obeyed, as we shall see later on. What is Hooke's law, or what does Hooke's law state? So for small extensions, we are seeing that the load is directly proportional to extension, that when we remove the deforming force, the material goes back to its original length. Similarly, at some points slightly beyond P, where P is going to be called the proportionality limit, proportional, that is a straight line. It is called proportionality limit because the load is directly proportional to the extension. But slightly beyond P, the load is no longer proportional to the extension. However, even when the deforming force is removed, the material goes back to its original length. So this point E is going to be called the elastic limit. Elastic limit. So beyond the elastic limit, we may not need to talk about the yield point, but beyond the elastic limit, we know that beyond the elastic limit, now the material stretches in such a way that even when the deforming force is removed, it does not return to its original length. So a graph of force against extension for a material such as copper is going to take that shape. So what is this shape, or what is special about this shape? So let's say beyond this point here, maybe the material breaks. I'll call this one the breaking point. Maybe this point is going to be called the breaking point. What is special about copper? Copper behaves in such a way that, one, for small loads, the load will be directly proportional to extension. So it stretches directly proportional to the load if the load is small. Number two, you can stretch it beyond the limit of proportionality, but still when you remove the deforming force, it goes back to its original length. Number three, if you use extremely large loads, remember the load is no longer directly proportional to extension, that is after E, or after the elastic limit. But when you remove the load, the material will not go back to its original length after point E. So we shall later on say the material has undergone plastic deformation. So after this point, the material has undergone plastic deformation. Here, beyond E, the material has undergone plastic deformation. But before E, the material is undergoing elastic deformation. So we now have two terms to talk about here: elastic deformation and plastic deformation. Okay, so it is going to be linear, it is going to be very convenient for us to consider number one, the gradient of the straight part, the straight line part of this graph. What does the gradient stand for? This is a graph of load against extension, and a straight line means that the load F is directly proportional to the extension. So F is directly proportional to the extension. So when I introduce a constant, equal signs and a constant means the load F is equal to a constant times the extension X. So it means if this is a gradient of F against X, where X is the extension, it means the gradient is going to be equal to the gradient is going to be equal to of course the change in f over change in x, which is going to be equal to k. So in this case, the gradient is going to be equal to the constant of that material. If it is a wire, it is the constant of the wire. If it is a spring, we would call it a spring constant. So this could be called the force constant of the wire. So because for the straight line, the load F is directly proportional to X. Removing a proportionality sign and introducing a constant, F is equal to Kx. So if we have F on the y-axis and X on the x-axis, comparing with the equation y equals to mx plus c, because the graph goes to the origin, there is no y-intercept. On the y-axis, I have F. On the x-axis, I have extension. So the gradient is going to be K. And we are saying that gradient is going to be called the force constant. So the gradient is the force constant. It is normally going to be convenient for us to plot a graph of F on the x-axis and E on the y-axis. This is because we normally change F, which is going to be the independent variable, so that we get E, which is the dependent variable. Normally, it is easier for us to plot to put the independent variable on the dependent variable on the x-axis and the independent variable on the y-axis. But that is not really normally the case. If we are changing f to give a change in x, or to give a change in the extension, then many times it is better for us to sketch E against F rather than F against E. Even though we are changing F, which is F is the independent variable because it must be changed by the experimenter, and E is the dependent variable because it depends on if we have changed F. So many times it is going to be you are going to see graphs of E against F or F against E, but the shape is almost the same, only that many times it is going to be bending towards the extension axis as shown in this graph. If the extension is on the vertical axis, it may bend upwards. So it is normally convenient to plot F on the x-axis and E on the y-axis because F is independent, whereas E is dependent. Just like when you are plotting graphs in math, the x coordinates are the ones which are actually dependent, and the F coordinates, I mean the y coordinates, are the independent. So for those of you who are doing both AS and A level, you will understand what I mean by dependent and independent variable, especially when it comes to paper 5. Normally, when you are telling the examiner which graph to plot, you always prefer to tell the examiner that the independent variable is going to be on the x-axis and the dependent variable is going to be on the y-axis. And if we had to sketch a graph of E, if we were to sketch a graph of E against F, because E is the dependent, F is the independent, is the one we are changing, then it will initially also be a straight line, but then it will go upwards like that, you know. So in that case, the gradient would be the reciprocal because it's now E against F. So it means the gradient of the straight line part is going to be 1 over K. So in that case, the gradient will be the reciprocal. So whenever I have a graph of E against F, the gradient is going to be just the reciprocal. Okay, so let us try to explain this graph. Let's try to explain this graph first of all. For the section of the line from the origin to point P, where the line is a straight line, we say the extension is directly proportional to the load. And we are saying P is the proportionality limit. E is going to be called the limit of elastic behavior or the plus elastic limit, and is usually slightly beyond P. It is usually slightly, just slightly beyond P. Of course, for learning purposes, the space between P and E has been exaggerated, but is just slightly beyond P. So the material is deformed permanently, and the change is going to be called plastic if we consider any points beyond E. So what happens beyond E? Imagine you are stretching a polythene material or a polythene bag. If you stretch a polythene bag, you even see that the material, as it stretches, you even see that the thickness of the material decreases because the molecules are sliding past each other. So beyond E, it's like the molecules which make up the material slide past each other to new positions, and the material is going to be permanent, or is going to be said to be permanently deformed. So the deformation is going to be considered irreversible. So we shall call it an irreversible deformation because the material goes to a new position, or the particles which make up the material move to new positions and maintain or retain those new positions. So the material is going to be considered to be permanently deformed, or we can say the deformation is irreversible. So for any material under plastic deformation, the material will not return to its original or its initial shape or its initial length or its original length, even when we remove the deforming force. So if you overstretch a material by putting an extra or excess load, removing the load would mean that the material remains in its new position, or the material retains its new length even when you remove the deforming force. And that's what I'm saying, what I'm calling the material to be plastically deformed. So now we know the difference between elastic deformation and plastic deformation. Okay, I'll not talk about the yield point, but to yield is like to slide past each other, where the particles start sliding past each other. Okay, so I gave a simple explanation here for that graph. For the section of the line from the origin to point P of the proportionality limit, where the line is straight, we say the extension of the spring is directly proportional to the load. In other words, F is directly proportional to the extension. Many times I'll use E or X to mean extension, many times. And E is called the limit of proportionality or the limit of elastic behavior, and I'm saying it is usually just beyond point P. So the material is deformed permanently, and the change is said to be plastic for points beyond E. So after E, the change is going to be considered plastic. So what happens after E is that the molecules slide past each other to new positions, and the material is deformed permanently. So the molecules slide to new positions and they retain the new positions. The molecules retain their new positions, so it means they don't move back their original positions. So in that case, we say the material has undergone plastic deformation. So when someone talks about plastic deformation, it means the material does not return to its initial length or original length or shape or size when the deforming force is removed. The material does not return to its initial length or size or shape when the deforming force is removed. That's what we call plastic deformation. And by the way, even though we are not supposed to talk about this, such a material is going to be called ductile. For examination starting from 2022, you don't need to know about the different types of materials, but such a material is said to be ductile. Any material which undergoes uh, both elastic deformation and plastic deformation before breaking is going to be considered ductile. So the one we have discussed previously, that is copper, is going to be ductile because copper, we have seen from the graph, it can undergo elastic deformation, then it will undergo plastic deformation, and then it will break. So such a material which undergoes both elastic deformation and plastic deformation before breaking is going to be called ductile. Of course, such a material is very useful. It can be molded into several shapes without breaking. So copper and gold are common examples of such ductile metals because they can be shaped by stretching, they can be rolled, they can be hammered, they can be squashed into several shapes, which makes them useful for wires like the ones we use at home for electrical wires, jewelry, and thus they are said to be ductile. So copper and gold are common examples of materials which can be molded into several shapes because they can undergo both elastic and plastic deformation without breaking. So those are ductile materials. Let's try to understand plastic deformation in more details. Plastic deformation. So let's consider a material which has undergone plastic deformation. What happens to the material when the deforming force is removed? So we said when the deforming force is removed, if a material is loaded, for example, let's say the material is loaded in, let this be a graph of force against extension for a material which has been loaded not beyond the elastic limit. So if this is loading for such a material not beyond the elastic limit, so let this be the proportionality limit, and this is the elastic limit. If the material has not been loaded beyond the elastic limit, if this arrow shows loading, if the deforming force is removed, the graph will just follow the same path and go back to original length. So this will be unloading. As the load is removed, the extension decreases until it goes back to zero. This is for elastic deformation. But for plastic deformation, we notice that when the loading takes place beyond the region of or beyond the elastic region or beyond the elastic limit, for example, it undergoes plastic deformation, and when the deforming force is removed, we notice that some extension is retained. This extension remains. So this extension has remained even when the material has been unloaded. Some extension remains. So it means the material has undergone a plastic deformation. So when the force is decreased back to zero, there is still some extension. So the area under the curve up to this point with the x-axis will be the work done in loading. The area under this line which goes downwards will be the area under unloading. So the area which is trapped here is the energy which is wasted as maybe thermal energy. The energy which is maybe absorbed by the material, the energy which becomes internal energy, which is the work done between loading and unloading. That is the difference between the two. You get the area of the whole curve with the x-axis. Of course, the area is obtained with the whole axis. So if I call this A and I call this one B, so loading, the work done in loading, I'll call that one work 1 will be B plus A. And the work done in unloading will be A. So it means the work which is wasted, maybe as heat, therefore B plus A minus A, which is going to be B. So that's the work which is wasted as heat. So this is how the material behaves. There will be an extension which is not returned when the deforming force is removed. And such a material is said to have undergone plastic deformation. There is still some extension even when the deforming force has been removed. That's what we call plastic deformation. Okay, so let us understand elastic limit and Hooke's law in more details. So we have mentioned that at the elastic limit, or the body undergoes elastic deformation if, when the deforming force is removed, the material returns to its original length. And that point we call the elastic limit. So what is the elastic limit? It means there is a point beyond which the material will no longer return to its original length if the deforming force is removed. And that point is going to be called the elastic limit. We can explain it in terms of force as being the maximum force that can be applied onto the wire or onto a material, such that when the force is removed, the material goes back to its original length, or beyond which, when the force is removed, the material does not return to its original length. So that's going to be called the elastic limit. So it's going to be called the maximum force that can be applied to a wire or a spring or a material such that the wire returns its original length when the force is removed, and beyond which the wire or the spring or the material will not return to its original length. So if we apply a force beyond the maximum, it means the material will not return to its original length even when we remove the force. But if we apply up to that maximum, then it means the load will return to its original length when the material will return to its original length when the force is removed. So that's what we mean by elastic limit. The maximum force that can be applied to a material such that the material returns to its original length when the force is removed, beyond which the material will not return to its original length. Sometimes we may just quote a point, but it is actually referring to a load or a force. A point beyond which the material does not return to its original length when the deforming force is removed. That's what we call the elastic limit. So we said for small extensions, the load was directly proportional to the extension. For small forces, we saw that the extension was directly proportional to the load, which gave us a straight line. And this therefore leads us to what we call Hooke's law that you mentioned in IGCSE. So Hooke's law states that provided the limit of proportionality is not exceeded, we should not exceed the limit of proportionality. That's why in the previous graph we said Hooke's law was obeyed in that region where we had a straight line. Provided the limit of proportionality is not exceeded, the extension of a material is directly proportional to the applied force or to the load. This is not to the applied mass, it is to the applied force or to the applied load. If the proportionality limit is not exceeded, that is just true for small extensions or for small loads. If the limit of proportionality is not exceeded, the extension of a material is directly proportional to the applied force. If the limit of proportionality is not exceeded. So we can put this in mathematical terms. So force, which is the load, is directly proportional to extension. Like I said, I will always use X or E for extension. So removing the proportionality sign and introducing equal signs, F is going to be equal to Kx. So many times I will say from Hooke's law, F is equal to Kx, where F is going to be the tension, it can be the force acting on the spring, or it can be the deforming load, and so on and so forth. And then X is going to be the extension, which could be the new length of the material minus the original length. L is the unstretched length, which is the original length. Then L is the stretched length, that is the new length, and L naught is going to be the unstretched length, that is going to be called the extension when we subtract L minus L naught. And then K, of course, K is a constant, which is called the force constant, which could be the gradient of the graph that we saw above. If it is a spring, we can call the spring constant. If it is just a wire or any other material, we just call the force constant. Remember, if you sketch a graph of F against extension, F against extension, if a Hooke's law is obeyed throughout, it's going to be just a straight line. And we saw that the gradient of this graph, the gradient of that graph was equal to the constant K, which is the force constant. So if from F is equal to Kx, we notice that K is equal to F over X. If we want to tell the units for the constant K, we know that F is in newtons and the extension is going to be in meters, so the units are going to be newtons per meter. So the units of the force constant are newtons per meter. But of course, in the first unit of AS physics, which is base units, we can also express this in base units. Remember, 1 Newton, Newton is force and force is mass times acceleration. So the units of force would be the units of mass, which is kilograms, times the units of extension, times the units of acceleration, which is meters per second. So that is force. Then divide this by, meters per second squared, that is force, which is mass times acceleration. Then divide by x, which is meters. So it means Newton per meter is the same as kilogram per second squared. That is in base units. Newtons per meter, because a Newton is not a base unit. It is a unit of force, but force can be expressed in base units, which will be kilogram meters per second squared, because force can be mass times acceleration. So the base units would be kilograms per meter, kilograms per second squared. So those would be the base units of force or of the spring constant K. We need to note a few things from what we have just explored. Some of the things we need to note would include the following. Number one, the force constant or the spring constant K can only be obtained from the gradient of the straight line section. That's where Hooke's law is obeyed. From any graph of force against extension, if we want to get the force constant or spring constant of the material, we just look at the gradient of the straight line section of the graph. Number two, in case the graph of force extension is given for a specific material, we can sometimes prove if Hooke's law is obeyed by checking if there is no y-intercept. Because if there is no y-intercept, means one, the graph goes through the origin. For all values, when x is 0, f is 0. Then calculating the gradient using coordinates of one point on the line and putting it in the equation y is equal to mx plus c, we should be able to see that the y-intercept is 0. If the y-intercept is 0, it means f is perfectly directly proportional to x. C is only going to be 0 if the line passes through the origin. So if c is equal to 0, that means if there is no y-intercept, then the line passes through the origin. That means has no y-intercept. And so we can say force is proportional to extension, meaning Hooke's law is obeyed. So Hooke's law is going to only be obeyed if the graph has no y-intercept in that case. That would mean the load is perfectly directly proportional to the extension. For Hooke's law to be obeyed, the graph must go through the origin. This is very important. If the graph of force against extension does not pass through the origin, Hooke's law is not obeyed. So if a material is stiff, a stiff spring, for example, or material will have a large value of force constant K. And if a material is stiffer, it requires more force to give a small extension. So a force against extension graph will appear steeper. So what do I mean by this statement? Some springs could be perfectly identical and have the same length. Let's we have spring A where we attach say at 20 grams, and we have another identical spring B, and when we attach 20 grams it stretches to that point. So consider spring A and spring B. The same 20 grams has caused a smaller extension for spring A, but the same 20 grams have caused a bigger extension for spring B. So we would say B is less stiffer than A, or A is stiffer than B, because for the same load, B stretches much more. So from constant K equals to the load divided by the extension. The load is the same, But for A, the same load is causing a smaller value of E. And for B, the same load is causing a bigger value of E. So it means K is smaller for because E is smaller for A, it means K is bigger. Because E is bigger for B, it means K is bigger. So for example, I will put numbers here. So let's say this is causing an extension of 2 centimeters and this is causing an extension of let's say 4, because this is bigger than the other one. So the K for A is going to be the load. I'll just use 20 times G, or 20 grams, or 20 times G, not 20 grams. So 20 times G divided by the extension, which is 2. And then for B, I'll say K to B is going to be 20, say, times G divided by 4. So this one will be equal to 10 times G. This one will be equal to 5 times G. So it's like a material which stretches very easily, is less stiffer. It has a smaller spring constant, a smaller constant. So for a material which is hard to stretch, it has a bigger constant. So it's like there's a relationship between the stiffness and the force constant K. So I'm saying a stiffer material will have a large value for the force constant. It doesn't stretch easily. A stiffer material will have a large value for the constant. So any material which has a bigger value of the constant will not stretch easily. In the laboratory, you should be having several different types of springs. There are those which are easy to stretch, and there are those which cannot easily be stretched. Those which can't easily be stretched will always have a bigger constant, which we call the force constant or the spring constant, and those springs are going to be called stiffer. Any material which cannot easily be stretched or strained is going to be called stiffer, or a stiff material. Okay. So that is a good introduction. We have talked about Hooke's law. We have talked about force against extension graph. We have talked about elastic limit. We have talked about elastic deformation and plastic deformation. So having understood Hooke's law, elastic limit, and plastic deformation, now we are going to investigate springs. These you can do them in your school. As a teacher, you can try to investigate springs in class with your students to understand this in more details. So if a spring regains its original length when the deforming force is removed, then it is said to be stretched or extended elastically. We have already mentioned that. And if the spring does not return to its original length when the deforming force is removed, then it has undergone plastic deformation, or it is plastically deformed, or it has been extended plastically. So this is an activity I expect you to organize in your class. Use identical springs. Measure the force constant of a single spring and of two springs in a series. What I mean by series, join them end to end. So you have one spring, you have obtained its force constant. Now you have two springs in series, you obtain their constant, that is in series, and in parallel. In parallel, I mean you now have them in this nature. Sorry. In parallel, I mean you now arrange them like this and put your object, the same load. So this is an activity you can carry out in class. Have identical springs. You can even have 1, 2, 3, 4, 5 springs, and put all of them on the same retort stand. Clamp them on the same retort stand, add the same load. Put the same load on each combination and see what really happens. Of course, what I expect is that if this extends by 2 centimeters, I expect this to extend by approximately 4 centimeters, and I expect this to extend by approximately 2 divided by 2, approximately 1 centimeter. This is what I expect. In other words, if you have more springs in parallel, the extension will be as much smaller as the extension of just one. they will be less than the extension of a parallel system will always be less than the extension of just one spring. But if you join them in series, you'll notice that the extension of the total extension becomes just goes on increasing. The system becomes easier to stretch every time you connect them in series. What does that mean? It's like when I have springs in series, the force constant K becomes smaller. And when I have them in parallel, the force constant K becomes bigger for the whole system. So why is the force constant smaller in series? And why is the force constant bigger in parallel? So if they're in series, the force constant becomes smaller. And if they're in parallel, the force constant becomes bigger. How do we make a quantity bigger? Many times it's going to be by addition. And how do we make quantity smaller? Is many times it's going to be by using the reciprocals, as we are going to see, but we shall investigate that. So you can try to predict the outcome before doing the experiment. Suppose the force constant of a single spring is K. What would be the equivalent force constant of A? Two springs in series and two springs in parallel. You can try to see to predict what happens. Me, I'm predicting that if this force constant of one spring is K, most likely if there are two in series, the force constant is going, because it should decrease, it is most likely going to be K divided by 2. If there are 3, it's going to be K divided by 3. If there are 4, it will be K divided by 4. And I'm predicting that if they are in parallel, because the force constant increases, then if there are 2, it is most likely going to be 2K. If there are 3, it is most likely going to be 3K. 4, it is most likely going to be 4K, and so on and so forth. Because in parallel, it becomes harder to stretch. That means the force constant increases. In a series, it becomes easier to stretch, which means the force constant decreases. Okay. Then now you can try more combinations. Try to apply to a combination of 3 or more springs. So you can do this activity in your class. Me, I will just take you through the mathematical concepts involved here, and I give you just a clue. So let's begin with the springs in. We are going to consider springs in series. Let's consider two springs joined in series, that is side by side. We are going to assume that if we have one spring used independently or one spring which is used alone, I think I should use yellow here. If I have one spring used alone, let's say its spring constant is K. Then if they are identical, if it is used alone, its extension, let it be X. So of course, by Hooke's law, F is going to be equal to K times X. That is the tension in this spring here. Now here I have two springs. Let us begin by assuming that they are not identical. Of course, in the exam, you'll always have identical springs. For examination purposes, most of the questions will consider identical springs. So what is the tension in each of these springs when they are loaded with a mass, with a force F, or when they are loaded with a load F? So if these springs are identical, it means the tension which the bottom spring experiences is the same tension which the upper spring experiences if the weight of the bottom spring is negligible. So assuming we ignore the weight of the bottom spring and just we are considering the load F which is attached, it means F1 and F2 are going to be the same, and they are going to be the same as F. The tension in the first spring is going to be the same as the tension in the second spring, which is going to be the same as the load applied, which is F, for equilibrium in that case. Of course, tension is given by Hooke's law. The force, which is the tension, is going to be F times Kx. Therefore, the tension in both springs is the same and is equal to the load which is applied, and that means F1 and F2 are going to be the same, and they are going to be F. But if we add the load F, the first spring will stretch with extension X1, The second will also stretch with extension x2, so that total extension is the sum of the two. So total extension of the springs is going to be the sum of those extensions. So for springs in series, total extension is going to be the sum. The system becomes easier to stretch, so it overstretches if they're in series. But if we consider Hooke's law, then F is equal to K total, which is total extension times, total constant times total extension. So if I make a total extension the subject, X total is going to be F over K total. So for x1, it is going to be F over K1. Remember, F1 and F2 are the same as F. And for x2, it is also going to be F over K2. So I just combine the two equations. If I combine the two equations, I am combining this one here with this equation here. So it means, these equations, this one, and that one there. Where there is x total, I have F over K total. Where there is x1, I'm putting F over K1. Where there is x2, I'm putting F over K2. It gives me a 1 over K total as being equal to 1 over K1 plus 1 over K2. For examination purposes, I say the springs are always going to be identical. And if they're identical, the constants K1 and K2 are the same. In that case, if the springs are identical, K1 and K2 are the same. Let's say they are just equal to K. So it means total constant therefore becomes 1 over K plus 1 over K, which is 2 over K. And of course, we get the reciprocal. And if we get the reciprocal, it means for springs in series, total constant is the constant of one spring divided by the number of springs if they are identical. For springs in series, if they are identical, total constant is going to be the constant of one spring divided by the number of springs. If the springs are not identical, but they are just two, the total constant is going to be the product K1, K2 over K1 plus K2. If they are not identical, but they are just two, just the product over the sum, the way we deal with our resistors in parallel. The way we deal with resistors in parallel is the way we deal with the springs in series. Just the way we shall deal with our capacitors in series. So if springs are in series and they are not identical, you can find total constant from the product over the sum if they are just two. If there are so many, then we can find total constant from 1 over the reciprocals of all those springs. If there are so many and they are identical, then I will say total constant for so many springs, if they are identical, will simply be K divided by N, where N is going to be the number of springs in that case. Okay. So if we have 3 springs in series and identical to be K over 3, we have 4 springs in series and identical to be K over 4, and so on and so forth. So we are saying the system becomes easy to stretch, that is less stiff, as we add more springs in series. So the spring constant will become smaller. So for springs in series, the system becomes easier to stretch, and therefore, any material which is easier to stretch is less stiff. We say the spring constant is smaller. Okay. So that is for springs in series. Let's see the springs in parallel. So let's consider 2 springs in parallel joined side by side. Of course, if they are joined in parallel, then if initially they are not identical, so they are going, first of all, when they are going to have the same horizontal, the same vertical extension. Of course, if they were not identical, if one stretches by extension, let's say 2, and another one stretches by extension, let's say 4, when you use both of them, the total extension will be even smaller than 2. It will always be smaller than the extension of the smallest extension, experienced by one spring. So if you use them together, it's like they share the load. they share the load in the ratio, of course, of their stiffness, or in the ratio of their constant. So it's like the load F is shared among the two. So it's like F is going to be what the first spring takes and plus what the second spring takes. So if they're in parallel, they share the load. The load is shared between the springs, but the spring extends by the same amount because it will be the same. The effective extension is going to be the same in the vertical. So it's like the extension is considered to be the same. But you will notice that the one which is extremely stiffer determines how far the extension X goes. The one which is stiffer determines how far the extension X goes, because it is the one which would limit the value of extension X. So if we have springs in series, I mean in parallel, the load F is shared so that F is equal to F1 plus F2. And if I use Hooke's law, remember F is equal to K times X. So if F is the effective load, then this is going to be total constant times total extension X. So that is going to be, I think I need to change the color to maybe blue. So by Hooke's law, F is going to be equal to KT, where KT is total constant, times X, which is X is the effective extension, which means for F1 it will be K1 times X, and for F2 it will be K2 times X. So mark the difference between series and parallel. For parallel, the extension is the same, and for series, the load was the same. The experienced load was the same. So I'm now just going to combine these three equations, 1, 2, 3, into the first equation here. So when I combine those three equations, where there is F, I put K total times X equals to K1X plus K2X. And because X is the same, then it means K total is equal to the sum of the constants. So if you have springs in series, total constant is the sum of the constant of the spring constant. If you have so many in series, it will mean total constant will be equal to K1 plus K2 plus K3 and so on until you reach plus Kn, where n is the number of springs that you have. If the springs are identical, then it means K1 and K2 are the same. Since they are only two, and K1 and K2 is the same, it means the total constant is going to be K plus K, which means total constant is going to be twice K if they are identical. If you have so many springs which are identical and in parallel, then total constant K total will be K plus K plus K until you reach the last K. So until you reach nk. So it means total constant is simply going to be n times k if they are many and they are in parallel. If I have 4 springs in parallel, it will be 4k. If I have 5, it will be 5k, and so on and so forth. And since the constant is bigger and is becoming bigger and bigger as we increase the number of springs, it means the system becomes harder to stretch as we add more springs in parallel. So it means the system becomes harder to stretch, it becomes stiffer as we add more springs in parallel. So for springs in parallel, stretching the system becomes even harder for springs in parallel. Okay, I would wish to give an example, but I'll give an example at the end. Okay, so before we look at force extension graphs for other common materials, let's first see some examples about combination of springs. I will have springs. Let's say I have 1, 2, 1, 2. I'm going to consider these springs being identical and a load F is attached to them. Let's say if we have one spring, if it is used alone with the same load, with an identical load L, the constant is K and extension is E if it is alone. So we want to find the total constant here and total extension. So I want you to note that these two are in series. These two are in series. We have seen if springs are in series, total extension is going to be, this will be twice E. These ones will also be twice E. So you now have two springs. This is equivalent to having one spring and another spring in parallel, where this is 2E and this is 2E. So if you have two springs in parallel, we have seen the total extension becomes half of the extension of just one. So this means total extension here is going to be just E. So the total extension of the whole of this system is going to be E. Then how about constant? Spring constant. So the spring constant for two springs in series was K over 2. This will be K over 2. And this was also K over 2. Now you have two springs which are in parallel, where this is K over 2 and this is K over 2. So what is the total? We have seen that when springs are in parallel, total constant is got from sum. So total constant K total will be K over 2 plus K over 2, which means it's going to be 2K over 2, which is simply going to be K. So it means the whole system has total extension as E and has total constant as K. When you watch my solve the past paper questions, there's a simpler hint that there's always a relationship between the coefficient in front of the total constant and the coefficient in front of the constant. Normally, the coefficient in front of the total constant is the reciprocal of the coefficient in front of the total extension. Let me give another one to verify that. Let's say we have one spring here in parallel, and then we have another one here with the same load. So if it is used alone, each has an extension E. Now these two are in parallel. And if they're in parallel, total extension is going to be just half of the extension of one. So extension for this is going to be E over 2. But this is alone, so it is going to be E. So we have E is in series with E. I mean, E over 2 is in series with E, which means total extension is going to be E over 2 plus E, which becomes 3E over 2. So that will be total extension. Then a total constant. These two are in parallel. For springs in parallel, total constant is the sum of the two, so it is going to be 2K here. But 2K is in series with this one, which is K. 2K is in series with K, and if you have springs in a series, total constant is got from the reciprocal, so this will be 1 over 2K plus 1 over K. So it means 1 over K total is going to be equal, the LCM is 2K, so this is going to be 1 plus, this is going to be 2. So this becomes 3 over 2K. So when I get the reciprocal, I get K total is equal to 2 over 3K. Now I want you to look at total extension here and total constant here. It's like if I can find total extension, then the total constant, I just change the reciprocal of the coefficient of total constant, because this is 3 over 2e and this is 2 over 3k. This was showed to us by one of my students. So you can use that simple analogy when you are solving such questions which involve combination of springs. There is a relationship between the coefficients of the total extension and the total constant. And of course, this comes from Hooke's law, where force is directly proportional to extension, which means K is inversely from F equals to Kx. It means K is inversely proportional to the extension. So the coefficient is going to be, the coefficients are going to be the reciprocal. Okay. So let's talk about force extension graphs for other materials. I will need this space here, so I have to wrap this space. So let's consider glass. We are going to talk about glass and rubber as common materials. So glass stretches slightly and suddenly breaks. That one we are much aware. Glass and ceramics or clay, it stretches suddenly and it breaks without giving warning. So it means it just stretches to its breaking point without undergoing plastic deformation. And such a material which stretches to its breaking point or it breaks without giving warning is what we call brittle material, as opposed to the ductile material that we discussed before. So brittle materials show elastic behavior. In other words, they stretch up to the breaking point. So if I was to sketch a graph of glass, force against extension for glass, it would be a straight line up to the up to the breaking point. So it just undergoes elastic deformation and it breaks as soon as the elastic limit is exceeded. That is glass. That's its nature. It's the same thing with the ceramic materials such as clay or materials made from clay. They will stretch up to the breaking point and suddenly break. Those materials are said to be brittle, as opposed to the ductile materials which first undergo elastic, then plastic before they break. Another common material that we are going to talk about is rubber. Rubber is the most common material you'll always find in your exams. Rubber. How does rubber behave? Now for rubber, it behaves differently. We know that rubber will not easily break. Many times it doesn't break unless you overstretch it. If you have tried to stretch a rubber band, you might have noticed that initially it is hard to stretch, but it becomes very easy to stretch after a short extension. And when you overstretch beyond a certain point, it again becomes harder to stretch. And of course, if you stretch further, it just breaks. So initially, it is hard to stretch. After a small extension, it becomes easy to stretch. And after it has stretched many times, again it becomes harder to stretch. Such a material is said to be a polymeric material. Polymeric materials are the ones which behave like that. Initially, they are hard to stretch, but when they have slightly stretched, they become easy to stretch. And after they have stretched many times, it becomes harder to stretch them again. But by the way, when you remove the deforming force, the material will not follow the same path to equilibrium position. It will not follow the same path to its original length. Instead, it may jump following a different path to its original length. And such a behavior is what we are going to call elastic hysteresis. So rubber is unique because it shows a property which we call elastic hysteresis. So rubber is a polymeric material. You might be knowing several polymers if you're a chemistry student. It is a polymeric material. After a small initial extension, a rubber cord becomes easy to stretch. But when it is many times its initial length, it again becomes harder to stretch. And if you overstretch, it just breaks. So initially, you need initially you apply a bigger force to cause a small extension. But later on, you notice that the change in force is now smaller, causing a very big extension. And finally, you will notice now again, what is happening is that you will need more force. You will need more force to cause a smaller extension. So compare these areas here, these regions, these three regions. Initially, it is hard to stretch, but after small extension, it becomes easy to stretch. And when it has stretched many times more than its original length, again it becomes harder to stretch. That is the behavior of all polymers. So what is the difference between rubber and a wire? Of course, for a metal wire, it is not like this one here. So a good difference between a metal wire and a sample of rubber is that when stretching, the stretching force is removed, the rubber sample does not return to its original length by the same path. It will not go back to its original length following the same path as a metal wire does, not at all. The rubber will follow a different path to its original length, which will result into the rubber material warming up. So it means rubber returns to its original length but following a different path. Even though a copper wire, for example, may also return to its original length when stretched, just like rubber, as we have seen, for a copper wire, if the deforming force is not much enough to take it beyond the elastic limit, for it will return to its original length following the same path. But for rubber, it will return to its original length but will not follow the same path. And we are saying that behavior is called elastic hysteresis. So rubber shows what is called elastic hysteresis. Any material which returns to its original length but not following the same path is said to show elastic hysteresis. So that is now what makes rubber unique. It shows what we call elastic hysteresis. So let's understand what we mean by elastic hysteresis. So let's see what we mean by elastic hysteresis of rubber using this graph here. So when the rubber is loaded, the material follows this path. Initially, it is hard to stretch. It becomes easy to stretch after small extension. Then finally, it becomes again harder to stretch as seen by this curve, because we see that the change in extension again becomes smaller. That is loading. That's why you see the arrow is pointing in that direction. But when we remove the deforming force, the rubber will jump to its original length following a different path. So the total work done in loading will be the area under this curve with the extension axis. That is in loading. Then the total work done in unloading, the work done in unloading would be the area under the bottom curve. And we notice that the area is not the same, which means this area here, this is called the region of the hysteresis region here, is going to be the work done or the energy absorbed by the rubber, or the work done or the energy which is absorbed by the rubber, or the energy which is dissipated as heat, or which is the work done, the difference in the work done on loading and unloading. This one here, this represented by this region here. So this is called the hysteresis region, or which is simply the work which is not returned when the deforming force is removed, or the work which is not returned when unloading occurs. And by the way, this is the work which would make rubber very safe for use in other purposes, because it would reduce damage to a surface. If an object falls onto rubber material, then the damage would not be big, because not all the energy is returned. Not all the energy will be returned as kinetic energy. So if an object is maybe bouncing on a carpet which is made up of rubber, it means it will not bounce so high, because not all the energy which was stored on loading becomes kinetic energy. Part of it is going to be dissipated as heat within the rubber, which will warm up the rubber, rather than giving it to an object falling onto the rubber. Okay, so this is what we are calling elastic hysteresis. So elastic hysteresis is when a material is not permanently deformed, but when stretched, it does not return to the original length by the same path when the deforming force is removed. The material is not permanently deformed, but when the deforming force is removed, it returns to its original length following a different path. It returns to its original length or original shape or original size following a different path. And when the deforming force is removed, some energy is retained in the material. The energy is not reflected into changing the extension, but this energy is retained because not all the work which is done on loading is converted into other forms. So this energy is wasted as heat, which warms up the rubber material. And that's what I'm calling elastic hysteresis. That's what I'm calling elastic hysteresis. Okay. So to understand more about elastic hysteresis, I'm saying the area under the unloading graph, that is Y, is the energy which is returned when, or the work, the energy, the returned work or the returned energy when the load has been removed. And the area under the hysteresis section, which I've labeled X, is the work done when the rubber is the work done on the rubber which is not returned when the stretching force is removed. So X is not returned when we remove the deforming force. This work is what becomes a heat or internal energy in the rubber, and it will cause rise in temperature. If we want the total work done required to load the material up to the other point, then we would sum up those two. So the total area under the loading section, of course, when I talk about area, I'm referring to the area under the curve with the x-axis. If it is a graph of force against the extension, if it is a graph of extension against the force, it is always area with the extension axis. So the total area under the loading section is the work done in stretching the rubber material. So that's what we call hysteresis. I think we need to talk about a few examples and maybe we do a self-check or an exercise for us to reflect on what we have just learned. So a graph of stress against strain will take the same shape. So later on when we talk about stress and strain, we shall also sketch a graph of stress against strain for rubber. It will still take the same shape because later on when we define stress as force per unit area and the strain as extension of original length, we shall see that is equivalent to sketching force against extension, as we shall see later on. Self-check or examples. For the data given in the table, plot a graph of load against extension of the material. Use the data to determine the force constant of the material. So when I look at these values, if you were to sketch a graph of load, just pick a graph paper and try this out. You want to sketch a graph of load, which is the force, against extension. Of course, the graph is starting from 0, 0. And if you try to sketch this graph, let me see, the extension is increasing uniformly initially by 0.5, 0. Plus 0.5 plus 0.5 plus 0.5 up to here. So that means initially from 0 to around 4, it is going to be a straight line. 0 up to 2.0 is going to be a straight line approximately. Then after 3 point, when the force becomes 5, 6, now here the increase is 1.8. Then here the increase is 1.8, that is, what is that? 5.2 minus 3.8. This is 1.4. Then 7.8, 7.4 minus 5.2. This is 2.2. So it's like the extension now increases more rapidly. So that means the load is, this graph is going to curve downwards like that. So you can sketch that graph. And when they say use the graph to determine the force constant, so you are going to take the gradient up to where the straight line stops, just up to where the straight line stops. This is where you'll find the gradient, and this will give you the force constant, which is the gradient. So you can try to plot this graph on a graph paper just to gain confidence. So lastly, consider the force extension graphs for 5 springs. State State which spring has the greatest value of force constant. Force constant, the one which has the greatest value of K is the one which cannot easily stretch. It means it requires a big force to cause a very small extension because K is equal to F over E. It will require a big force to cause a very small extension, and that means the answer is going to be A. A is the greater is stiff because a very large force is causing a very small extension for A. Then B, part B, state which spring is less stiff. Of course, for less stiff, it means it requires a small force to cause a large extension, and that is going to be D. You notice that we have a small change in force has caused a very big extension for D. Then part C, state which of the springs does not obey Hooke's law. If it doesn't obey Hooke's law, it is not a straight line through it is not a straight line through the origin. So state which of the springs does not obey Hooke's law. So A automatically obeys Hooke's law. Then we shall start with D. We shall mention E. So we can consider A, B, and C to be obeying Hooke's law because initially they are straight lines through the origin. So we can take D and E. But however, for Hooke's law, it is supposed to be a straight line throughout. But of course, initially for small loads, Hooke's law is obeyed for A, B, and C, but it's not obeyed for E and D. Which spring undergoes both elastic and plastic deformation? So the one which undergoes both elastic and plastic deformation is automatically spring C because initially it is a straight line, then it undergoes plastic deformation. Okay, I think that one is a good exercise for us to understand the meaning of stiffness, plastic, and elastic deformation. So in conclusion, I want you to recall that when we determine the force constant of a spring, we are only finding out about the stiffness of that particular spring. And stiffness is the ability to withstand a deforming force or deforming forces. If a material is very stiff, it will withstand deforming forces very easily. That means it cannot easily stretch. That's what we mean by stiffness. You will not be asked to explain stiffness in your exams, but understanding stiffness helps us to deal with the combination of springs, for example. Okay, so I think that should be enough for lesson 1.